Hi there, this is Penelope and this is the second video in a short video just giving a couple of more examples of eigenvalues and eigenvectors. And as a summary, remember that we are working with finding the determinant or proving that the determinant of this is 0, and also we need to remember that I is this, and that therefore lambda times I is exactly the same, but it has lambda in each of the positions where the 1 was. Like that. So when we find A minus lambda times the identity, then we get the the characteristic equation, which in this case is 1 minus lambda, negative 1, 0, 1, 2 minus lambda, 1, negative 2, 1, negative 1 minus lambda. And we have to make sure that, because we're, it's all tied up with this, and remember that x as a vector is x1, x2, and x3, and that 0 is 0, 0, 0. We're given the eigenvalues and we're asked to find the eigenvectors. The first thing we would do is we would work with number 1. We would work with lambda being equal to negative 1, and that would give us the expression, putting it in matrix form, oops, that's a 1. So all I've done is I've substituted in lambda for negative 1. With a bit of playing around now, we can get that 2x1 minus x2 is equal to 0, which tells us we're just looking for the relationship between the variables, and also that x1 plus 3x2 plus x3 is equal to 0, which will give us that 7x1 is equal to negative x3. Now, an eigenvector that keeps these proportions is going to be x1 could be starting off with 1, and then x2 has to be twice that. Oops, should have a 1 there. So 2, and then 7. Oops, we should have a negative sign in there because x3 will be negative times 7 times x1. That's a negative sign in there. Okay, so now for the next ones. So now we've got that lambda 2 is equal to 1, and again we need to set up the matrix. And again, we just play around and find what we've got to find in combinations of x1, x2, and x3. And we get this one. And that allows us to find that x1 is equal to negative x3. So an eigenvector, not the an, just one, could be, so if it starts off that x1 is 1 and x2 we've found is 0, and x3 then will be the opposite of the first one, which would be -1, but it could be any constant times that. So whatever number times that. That's why we don't say it is the eigenvector, because we just could have any other number. Similarly for lambda 2, lambda 3 equals 2. Set up the matrix. And from row 1, -x1 minus x2 equals 0. So that gives us that -x1 equals x2, or x1 equals -x2, whichever is more useful. And from the second line, x1 plus x3 is equal to 0. So x1 is equal to -x3. So an eigenvector could be, so if x1 was 1, then the other two would be negative, or any multiple of that. So it could be 3, -3, -3, where I've just multiplied it by 3.